Welcome to the fascinating world of probability distributions. Imagine you are a scientist trying to predict the future, like guessing how many patients will recover from a disease or what the average height of a plant will be. By the end of this guide, you will understand exactly how to use the binomial, Poisson, and normal distributions to solve real-world biological mysteries. To begin our journey, let us understand what a probability distribution actually is. Think of it as a mathematical map or a cheat sheet for reality. It tells us all the possible outcomes of an experiment and exactly how likely each outcome is to happen. Instead of just guessing blindly, we use these distributions to make highly accurate, scientifically backed predictions in biostatistics. Whether we are looking at genetics, epidemiology, or ecology, we rely heavily on three main maps to guide us. Let us dive into the first one. Now that we know what these maps do, let us look at our first one, the binomial distribution. The prefix bi means two, reminding us that this distribution is strictly for situations where every single trial has exactly two possible outcomes, like success or failure. It is a discrete distribution, meaning we deal with whole numbers. For this to apply, four strict conditions must be met: a fixed number of trials, independent events, exactly two outcomes, and a constant probability of success. It is the ultimate tool for analyzing categorical data, where outcomes are strictly binary, like whether a patient survives or a cell mutates. This concept leads us directly to its mathematical form. Let us break down this beautiful formula piece by piece. The symbol P of x equals k represents the probability of getting exactly k successes. The letter n stands for the total number of trials we are running, while p is the probability of success on any single trial. The term 1 minus p represents the probability of failure. Finally, the binomial coefficient calculates all the different possible ways we can arrange those successes among the trials. If you increase the number of trials, n, the spread of possible outcomes becomes wider, and increasing p shifts the most likely number of successes higher. Before we move on, let us see this with a concrete example. Suppose a new vaccine has a 70% chance of successfully preventing a viral infection. A clinic administers this to exactly 5 patients. We want to find the exact probability that exactly 3 out of these 5 patients are protected. We chose the binomial formula because we have fixed, independent trials with binary outcomes. We plug in 5 for n, 3 for k, and 0.70 for p. Calculating the combinations and powers gives us 10 times 0.343 times 0.09. Multiplying these yields 0.3087. Physically, this means there is roughly a 31% chance that exactly 3 people will be protected. Having mastered counting binary successes, let us shift our focus to a different kind of counting problem. Imagine counting shooting stars or rare genetic mutations. Here, you do not have a fixed number of trials. Instead, you're looking at events that happen randomly over a continuous stretch of time, space, or volume. The Poisson distribution is designed exactly for this. It is a discrete probability distribution that helps us predict the likelihood of a specific number of events occurring in a fixed interval, especially when those events are relatively rare and unpredictable. You only need to know the average rate at which the events occur, making it essential for tracking disease outbreaks or endangered animals. This brings us to the mathematical engine behind these predictions. Let us look closely at the Poisson formula. P of x equals k is the probability of observing exactly k events in our chosen interval. The most important symbol here is the Greek letter lambda, which represents the average number of events that typically occur in that interval. The letter E is Euler's number, a mathematical constant approximately equal to 2.718, which naturally appears in growth and decay processes. Finally, k factorial means you multiply k by all positive integers smaller than it. If the average rate lambda increases, the peak of the distribution shifts to the right, meaning you are more likely to observe a higher number of events. Now that we have our formula, let us apply it to a real laboratory scenario. A microbiologist knows that, on average, 4 bacterial colonies grow per square centimeter on a petri dish. They want to find the probability that exactly 6 colonies will grow in a randomly selected area. We use the Poisson distribution because we are counting independent events over a fixed area with a known average rate. We set lambda to 4 and k to 6. Substituting these into our formula, the numerator becomes 4 to the power of 6 times e to the negative 4, and the denominator is 6 factorial. Evaluating this gives us 0.1042. This means there is roughly a 10% chance of finding exactly 6 colonies, helping the researcher understand natural random variation. We have explored discrete counts, but what about continuous measurements? Finally, we arrive at the most famous and widely used distribution in all of statistics, the normal distribution. If you measure the heights of every adult tree in a forest, they form a beautiful, symmetrical shape that looks exactly like a bell. Unlike the binomial and Poisson distributions, the normal distribution deals with continuous data that can take on any value, including infinite decimals. It is completely defined by just 2 parameters: the mean, which dictates the center, and the standard deviation, which dictates the width. Because of the central limit theorem, it is the absolute bedrock of biostatistics, allowing us to draw conclusions about entire populations from small samples. To draw this perfect bell curve, we use this mathematical recipe. The function f of x represents the height of the curve at any given value x. The symbol mu is the population mean, which shifts the entire curve left or right along the horizontal axis. The symbol sigma is the standard deviation. If sigma increases, the curve becomes flatter and wider, and if it decreases, the curve becomes taller and skinnier. The constants pi and e ensure that the total area under the entire curve is exactly equal to 1, which represents 100% probability. While this formula draws the curve, we usually use a simpler tool to calculate actual probabilities. This brings us to the practical way we actually use the normal distribution. Instead of plugging numbers into that complex exponential formula, we convert our target value into a z-score. The z-score tells us exactly how many standard deviations our value is away from the mean. The variable x is our value of interest, mu is the mean, and sigma is the standard deviation. By subtracting the mean from our value and dividing by the standard deviation, we are essentially translating our specific medical data into a universal statistical language. Once we have the z-score, we can easily use standard statistical tables to find the exact probability. Let us see how this works in practice. Now that we understand z-scores, let us analyze some patient data. Suppose the total cholesterol levels of adults are normally distributed, with a mean of 200 milligrams per deciliter and a standard deviation of 20. A doctor wants to know what percentage of the population has a cholesterol level below 220. We chose the z-score approach to standardize this continuous data. We substitute 220 for x, 200 for mu, and 20 for sigma. Subtracting gives us 20, and dividing by 20 gives a z-score of exactly 1.0. Looking this up in a standard table gives 0.8413. Physically, this means approximately 84% of the adult population has a cholesterol level below this threshold. To truly grasp what we just calculated, let us look at this visually. Here is the perfectly symmetrical bell curve representing our population's cholesterol levels. The horizontal axis shows the total cholesterol. Right in the center, at the highest peak, is our mean of 200. Notice the vertical line at 220, which is exactly one standard deviation to the right. The entire light blue shaded region represents all the people with cholesterol levels below 220. As you can see, this covers the entire left half of the curve, plus a significant chunk of the right side, visually confirming our calculated probability of 84.13%. This diagram perfectly illustrates how the normal distribution organizes continuous biological data. We have covered a lot of ground today, so let us summarize the most important ideas. First, the binomial distribution is your go-to tool for counting successes in a fixed number of binary trials, like testing a vaccine. Second, the Poisson distribution acts as a mathematical magnifying glass for tracking rare, independent events over time or space, like bacterial growth. Finally, the normal distribution is the ultimate model for continuous biological data, using its beautiful bell curve and z-scores to make profound statistical inferences. You now have the three most powerful mathematical maps in biostatistics to understand and predict the natural world. Great job following along!